Welcome! In this video, we shall continue on the Lagrange multipliers. We understood the meaning of the system of equations when we have an objective function and a constraint equation with two input variables. We can generalize the method of Lagrange multiplier to deal with constraint optimization problem when the objective function has n variables and there is one constraint equation. We still wish to locate points where the gradient of f equals to lambda times the gradient of g, which also satisfies the constraint equation. There will be a total of n plus 1 equations, and we want to solve for n plus 1 unknowns, x1 up to xn and lambda. These equations here are called the first order conditions, and this is the constraint equation. Let us refer to this example. We would like to find the maximum of the function x times y times ez subject to the constraint equation x plus 2y plus 2z equals to 12. Please pause and try it by yourself, and then we shall discuss it afterwards. In this question, we are given the objective function f of x, y, z equals to x times y times z, and the constraint equation x plus 2y plus 4z equals to 12. We can denote this part as g of x, y, z and c as the constant 12. By the Lagrangian method, we want to solve this system of equation, which the first order condition is gradient of f equals to the lambda times gradient of g, and the constraint equation g of x, y, z equals to c. Therefore, we first determine all the first partial derivative of the function f and g, and we set up this system of equations and solve for the unknowns. In this case, we get these four equations in a system. By using the first, second, and the third equation, it comes up to the condition lambda equals to y times z equals to x times z over 2 equals to xy over 4. Since we are asked to find the maximum of this function with x times y times z subject to this constraint equation, we observe that in order to have a maximum, we shouldn't choose the point where any of the x, y, or z is equal to 0, because it will give an output equal to 0, whereas there are still other points which satisfy this constraint equation, but having x, y, z to be non-zero, and they will give an output which is even higher. Therefore, we can assume that for a maximum to occur, any of the x, y, z shouldn't be 0. Therefore, when we consider this equation, we can cancel out the z to give y equals to x over 2. Similarly, if we consider these two expressions, we can cancel out the y to give z equals to x over 4. And substituting these two equation 4 gets x equals to 4, which help us to get all the other values. Therefore, we get one possible extremum point, which is at 4, 1, 2, and we get the output of the function to be 8 at this location. Now, since the constraint equation represents a plane in the three-dimensional space, therefore it means that it is possible that the function doesn't have any bound. Therefore, it is possible that in this case, we cannot find any absolute maximum of the function subject to this constraint. We check by trying other points which also satisfy the constraint equation to see whether we manage to get some output which is higher than 8. For example, we observe that if x equals to 72, y and z equals to -10, then this point still fulfills the constraint equation, but it gives an output 7,200, which is much higher than 8. Therefore, our conclusion is that there is no absolute maximum for the function x times y times z subject to this constraint equation.